So we're going to continue on here with flow networks, and let's establish a few, I don't know if it's a few definitions. I think I'll just be surprised when they come up, but yeah, I think two definitions. All right, so the weights on edges in a flow network are called capacities. And they're going to function that way, of course. That's why the name is what it is. All right, and then a flow is an assignment of numbers to edges. Okay, and of course we're going to call these flow numbers, and they should reflect something realistic and useful. So a flow is an assignment of numbers to edges that satisfies the following. All right, two rules. First of all, the flow number you assign can't be negative. All right, and it can't exceed the capacity. So I'm talking about an edge E here. So if my capacity was 7, then I could assign a flow number anywhere between 0 and 7. All right, and so that's rule 1. All right, this next one looks fairly complex, but the idea is quite intuitive, actually. Flow in at every vertex. The letter T snuck in there. Every vertex. Oh, that's how. ERT. Flow in at every vertex is equal to flow out at every vertex. Okay, I'll give you a few things to describe rule 2 in a few other ways too. Rule 2, again, I'm just redescribing this exact thing. This is called flows are conservative. There is exceptions to these, except, sorry, every vertex. I should say node. I have the vocabulary word, so let me correct it and say node. Flows are conservative at nodes. They're definitely not conservative at sources and sinks. So sources seem to create flow, and sinks seem to consume flow, right? And you can kind of adjust the metaphor based on what you want. All right, so another version of number 2. Again, there's just 3 versions of the same rule. This version is going to be like an equation form of this. So we have edges going in to a node. Take the flow in at a node, and we add up the flow going out. Again, take your node, look at the edges going out, the flow numbers going there. We add up the flow, these two numbers have to be equal. All right, let's take a look at an example of this here. All right, I'm going to bring back sort of the same friend, so if you were taking like notes by hand, you can reuse it provided you gave yourself enough space. Unfortunately, I need to make another version. My squeaky marker. I'm making it a little larger since there's more data that's going to be put on here. One thing that may not be consistent is the lettering, but I think I'll get it the same. This is 4, 4, 6, 1, 1, 6, 2, and 4. All right, get my directions. I'm doing this all in green because my flow, I'm going to use another color for that. So these are just capacities. These are the weights on the edges. So all of this is just the flow network is all in green. I'm going to do a flow in another color. All right. We're going to this is kind of going to be an allusion to what the process we're going to use going forward. But I'm not going to be quite so careful this time. All right, so I'm just going to try to obey these rules. That's it. All right, so let me start with this edge AB. The capacity is 4, so I could put a number anywhere between 0 and 4. Now we're going to, in the end, want to do a maximum flow. So let me just throw on a 4 here and see if I can make it work. Okay? It's the biggest number I can put there. All right, so this is saying essentially that 4 units of flow is going from A to B. Now B, since rule 2 has to be satisfied, I have to have 4 units of flow going out. And so just by the presence of this, I am forced to have a 4 here. I can't use this 1, it's going the wrong way. Alright, let's see. If I look at this edge AC, it has 4 capacity. Now thinking ahead, so I don't have to erase a whole bunch, notice that I do have 1 going down, 1 going up, and 2 going out. I could try to maneuver that, but let me do this. Let me do just 2. So when I get here, I can just do 2 straight across. Okay, so I don't have to split up my flow. Alright, down here, let me try 4 and 4. Right, 4 going into D and 4 going out. So right now it looks like I have sort of these distinct flow lines going across. So 4 on the top, 2 across the middle, 4 going down here. I can do a little better though. So what I'm going to do is I'm actually going to adjust my flow numbers because I can do this particular route here. So I'm going to bump this up by 1. And it's somewhat important in this example to realize I am intentionally being haphazard or a little bit kind of just improvising. So let's just check to make sure all the rules are satisfied, right? So all of my orange numbers are less than or equal to the green ones, right? So my flow numbers are less than or equal to capacity. And then I just need to check conservation. So I have 3 nodes to check. If I look at B, I have 5 units coming in, right? 4 plus 1 coming in, and 5 going out. So that's good. Let's look at C. 3 coming in, and 1 plus 2 going out. So that's good. And D, 4 coming in, 4 going out. So that's good. So I don't know if this flow is maximal or not. I suspect it is, right? You take a look, see if you can do better. I suspect it's maximal, but I don't know for sure, right? That aside, I do know it's a valid flow. It obeys rules 1 and 2. Okay, that's as far as we're getting so far. All right, so what other, I think we need to get a little more vocabulary here so we have some more tools for the next thing. Let me back to green. Let me draw another. It's pretty unusual to draw another version of this. I mean, for the purpose I'm using here. But I want to illustrate an important concept. Alright, so this is a flow network with flow on it. Alright, and it has vertices A, B, C, and D, and E, right? Let me get the directions. Alright, now I'm going to put new capacity numbers, and there's this thing referred to as the residual network, or the residual flow network. So you can say residual flow network, residual network. I'm just going to be lazy and say residual network. Alright, the interpretation here is not to take the original, but to take a look at what's left. So residual always means what's left. And you can see I've run out of capacity from A to B, and so the capacity on this edge is 0. Alright, from A to C, I've used up 3 of my 4 units, so there's 1 left there. Alright, and for there, it looks like I have 2 units left. I have 1 still going strong there. I have 0 going in that direction. 2 of 2 is used, so 0 in that direction. And 1 is left here, right? So I've used up 5 of the 6 units, so I have 1 left here. Alright, so this is the intuitive part of the residual networks, but there's more here, so let me see if I can illustrate that. Alright, so the trick is not to actually panic about... Okay, I don't want to use orange because I don't want it to be confusing, so I do need to use another color here. Let me pick the 2 edges that are connecting nodes to nodes. Alright, so there's also this notion of what you'd call backflow. Alright, its actual utility is anytime there's flow going in one direction, you have the option to turn that flow off. Now, of course, if you turn it off, you must turn it off conservatively. So this is the same notion as if you're going to turn a faucet on, you can turn it off. And this capacity to turn it off can be interpreted as a reverse flow number. Alright, so to turn off 4 units of flow in that direction, I can add 4 units of flow in the opposite direction, and that would turn it off. This is useful because if I just think of this as just continually adding flow on top of flow on top of flow, if I do it properly, I can turn things on and off as necessary until I've reached my maximum flow. So, for this one, oops, I don't even have a 0 here. I meant to have a 0. Maybe I said it out loud, maybe I didn't. Because I have 1 unit of flow going this way, I have the ability of adding a unit of flow in the opposite direction. Okay. Here I have the option of doing 4 units of flow in that opposite direction. And here, 2 units. And here's 5 units, right? So, and you can do these. I'll just go ahead and do them all, but it's kind of tedious. Here I can do 4 units in the opposite direction. Here, while I have 2 going that way, I can do 4 going in the opposite direction. 3 backwards. I don't need to put it, but I can. If I put 1 here, it would be 0. Right, there's no flow going in the right direction, so I can't do anything in the backwards direction. That looks like a 5. Hold on, let me correct this. It's the arrow and 0. Conspiring together. Alright, so I have 1 this way, 0 upwards. I think that's all of them. Yeah. This one is the one missing, sorry. 4. Backwards. Okay, so what's going on here? So residual capacity comes in 2 flavors. The forward, what's left, and you gain backwards residual capacity as you add flow forwards. If you add together these 2 capacities, the forward and backwards capacities, you should get back the original capacity. All right. That's a good rule of thumb. So always, if you notice all of these pink-ish or whatever color you see in pink or purple added to the green one, those are all equal to the original capacity number. Okay. We have to practice this a good bit, and I'm going to show you some demonstrations of how this works as sort of a physical interpretation. Because right now it's just a mathematical rule that seems somewhat strange. Okay. But as of now, you should focus on the orange a little bit, and then realize that this is going to be a thing going forward. Okay, you can certainly come back to this after you get a little more feel for backflow. Alright, so on the next one, yeah, we're going to start talking about flow augmentation. So it's the process of how to add flow, more and more flow to your flow network. And the occasion that we might need to use backflow, I'll bring it up and show you how to do it in a more practical sense. We don't draw this mess on top of flow networks all the time. And then we'll go back and we'll justify why that algorithm is working. Alright, so I'll see you on the next one when we work on that algorithm.